Mathematicians like to model uncertainty about a particular circumstance by introducing the concept of a random variable. For our application, we'll always be dealing with circumstances where there are a finite number n of distinct choices. So we'll be using a discrete random variable that can take on one of n possible values, x sub 1, x sub 2, and so on up to x sub n. The probability that x will take on the value x sub 1 is given by the probability p sub 1, the value x sub 2 by the probability p sub 2, and so on. The smaller the probability, the more uncertain it is that x will take on that particular value. Claude Shannon, in his seminal work on the theory of information, defined the information received when learning that x had taken on the value x sub I as the log base 2 of 1 over p sub I. Note that the uncertainty of a choice is inversely proportional to its probability, so the term inside of the log is basically the uncertainty of that particular choice. We use the log base 2 to measure the magnitude of the uncertainty in bits, where a bit is a quantity that can take on the value 0 or 1. Think of the information content as the number of bits we would require to encode this choice. Suppose the data we receive doesn't resolve all the uncertainty. For example, when earlier we received the data that the card was a heart. Some of the uncertainty has been resolved since we know more about the card than we did before receiving the data, but we don't yet know the exact card, so some uncertainty still remains. We can still use the formula for information content from the previous slide using the probability of the data we received to compute the information content. In our example, the probability of learning that a card chosen randomly from a 52-card deck is a heart is 13 over 52, the number of hearts, over the total number of choices. So p sub data is 13 over 52, or 1/4, and the information content is computed as log base 2 of 1 over 1/4, which figures out to be 2 bits. This example is one we encounter often. We receive partial information about n equally probable choices, each choice having probability 1 over n, that narrows the number of choices down to m. The probability of receiving such information is m times 1 over n, so the information received is log base 2 of n over m bits. Let's look at some examples. If we learn the result, heads or tails, of a flip of a fair coin, we go from 2 choices to a single choice, so the information received is log base 2 of 2 over 1, or a single bit. This makes sense. It would take us 1 bit to encode which of the 2 possibilities actually happened, say 1 for heads and 0 for tails. Reviewing the example from the previous slide, learning that a card drawn from a fresh deck is a heart gives us log base 2 of 52 over 13, or 2 bits of information. Again, this makes sense. It would take us 2 bits to encode which of the 4 possible card suits had turned up. Finally, consider what information we get from rolling 2 dice, 1 red and 1 green. Each die has 6 faces, so there are 36 possible combinations. Once we learn the exact outcome of the roll, we've received log base 2 of 36 over 1, or 5.17 bits of information. What do those fractional bits mean? Our circuitry will only deal with whole bits. So to encode a single outcome, we need to use 6 bits. But suppose we wanted to record the outcome of 10 successive rolls. At 6 bits per roll, we would need a total of 60 bits. What this formula is telling us is that we need not 60 bits, but only 52 bits to unambiguously encode the results. Whether we can come up with an encoding that achieves this lower bound is an interesting question which we will take up later in this chapter. To wrap up, let's return to our initial example. Here's a table showing the different choices for the data received, along with the probability of that event, and the computed information content. We've already talked about learning that the card was a heart. The probability of this event is 13 over 52, with an information content of 2 bits. Learning that the card is not the ace of spades is quite likely, since there's only 1 chance in 52 that it is the ace of spades. So we only get a small amount of information from this event, 0.028 bits. There are 12 face cards in a card deck, so the probability of this event is 12 over 52, and we would receive 2.115 bits. A bit more information than learning about the card suit, since there is slightly less residual uncertainty. Finally, we get the most information when all uncertainty is eliminated, a bit more than 5.7 bits. The results line up nicely with our and Mr. Blue's intuition. The more uncertainty is resolved, the more information we have received. Now try your hand at computing the information content for a few more examples in the following exercises.